Here we're going to talk about the third law of thermodynamics and also talk about the entropy of chemical reactions. All right, let's first look at the third law of thermodynamics. It's 3 or 4, depending on how you count them, laws of thermodynamics. Here's the third one. We already had the first two. And again, it's a law, which means that we don't derive it from principles, fundamental principles. In fact, it's just a generalization of everyday experience. So, third law of thermodynamics. So what we find, if you measure, for example, the entropy of a solid or entropy of a chemical reaction, you find that as you get closer and closer to absolute 0 Kelvin, the entropy of that reaction decreases, and it appears to approach 0. And you could further take this as not only the entropy of a chemical reaction, but the entropy of the actual chemicals, the products and reactants themselves, actually go to 0. So what you then, statement of the law of thermodynamics is that the entropy of a solid is 0 at absolute 0. Okay, so that's just extrapolation, but that's the third law of thermodynamics. And you sort of have a little fudge factor here, a little wiggle room. If you find that in fact the entropy of a solid is not 0 at absolute 0, then you say, oh, the entropy of that solid is not a perfect crystal. So this only applies for a perfect crystal, which means there's no defects in the lattice or anything. Okay, so that's one statement of the third law of thermodynamics. The entropy of a solid is 0, the solid being a perfect crystal, is 0 at absolute 0 Kelvin. Here's another statement of the third law. Remember that no engine is 100% efficient. So when we talked about heat engines, we said the heat engine, efficiency of a heat engine is 1 minus the temperature of the low temperature reservoir divided by the temperature of the high temperature reservoir. And experience has shown that this is always less than 1. So the efficiency is always less than 1. And again, this is not derived or anything. This is based on our experience. We never can get a 100% efficient engine in which you convert all the heat that we put in the engine into work. So this implies that the low temperature reservoir has to be greater than 0. In other words, if this term were 0, then the efficiency would be 1, but we never see that, therefore that term must be greater than 0. Okay, so absolute 0 cannot be obtained, because if it could be, then you could have a 100% efficient engine, and we don't see that. Another way to say that is that you cannot devise a way to lower the temperature to absolute 0. All right, so let's try to think of that. All right, so here is something that has, say, T greater than 0. And what you want to do is remove the heat, or transfer heat energy out of this until this can go to 0. Well, in order to do that, you need to hook that up to something that has T is equal to 0. So T to 0, you can suck out all the heat and make this T equals 0. But you can't have a T equals 0 if you're trying to get a T equals 0. So this implies that you cannot reach T is equal to 0 by any process in which you try to remove heat from a system. All right, so absolute 0 cannot be reached. So those are 3 statements of the law of thermodynamics. The one we'll use now is that the entropy of a solid is 0 at absolute 0. All right, so what does that mean? This implies that there is an absolute scale of entropy. So let us look at just not a chemical reaction, not the change in entropy, but just let's look at the absolute entropy of something. And this is temperature here, and we'll put this 0. The third law of thermodynamics says that at 0, the absolute entropy, not the entropy change for a chemical reaction, but the absolute entropy of a reactant or product is 0. Right there. And then if you increase temperature, as we said in the last lecture, the entropy will increase, and you'll have something like this. So let's say increase it to 298 room temperature. This means that, and how do you calculate these changes? Remember from the lecture that delta S can be equal to what? N times heat capacity times the natural log of the final temperature divided by the initial temperature, T1, or, a lot of ways to calculate it, or N can be, or delta S can be equal to Q reversible over T for a phase change, and so on. So you can actually calculate entropy changes. You start at 0 and calculate entropy changes as you heat up the substance, and say at there, at 298, that's the absolute entropy at 298. Well, you can look at it as an entropy change from zeros, but the entropy at 0 is 0. Okay, so that's a key point, that you have absolute entropies rather than changes in entropy. Now let's look at standard enthalpy of formation. So remember we talked about standard enthalpy, delta H, standard enthalpy of formation. That means you take the elements in their standard state, 25 degrees, like a gas or liquid or so on, and that'll be the reactants. And then you form the products. So these are the elements, and this is the compound. And delta H for that process is a standard enthalpy formation. But you're always referencing that to the standard state that we picked is the state of the elements in at 25 degrees. For example, the standard state of hydrogen will be H2 gas. The standard state of water would be water liquid, 1 atmosphere pressure, and so on. On the other hand, we don't need to reference anything here to a standard state because we know that the entropy is 0. Let's just see that. All right, so here's a Wikipedia article on the standard enthalpy change formation, or standard enthalpy formation, giving it a data table. So let's go down here and let's look at this table, this column. What we have here is standard enthalpy of formation. Note there's a delta there, standard enthalpy of formation, because it's the enthalpy of the compound minus the enthalpy of the elements in their standard state. On the other hand, if we do the same thing for standard entropies, note that there is no delta here. There's no delta. It's just S. It's just the absolute entropy of various compounds here. So that's interesting. So that's the point I want to get across, that now we have absolute entropies. We don't have to reference them to a standard state like we do for standard enthalpies of formation, or as we'll learn, standard free energies of formation, and so on. Okay, so that's the key point there. 3 statements of the third law of thermodynamics, and this is the important one we'll be talking about now. All right, now some textbooks have what's called a Zeroth Law of thermodynamics. So really there are 4. And you call this 0 because it really should be before the first law of thermodynamics. Zeroth Law of thermodynamics has to do with temperature, and it's nice to be able to talk about temperature or define temperature and have some idea what temperature is before you start introduce it in the first law of thermodynamics. The Zeroth Law was figured out after the first law, the second law, and the third law, but it really should come before the first law, so therefore they call it the Zeroth Law. All right, so the whole point here is that if you have thermal equilibrium between 2 states, or 2 systems, sorry, 1 and 2, and 2 and 3, then the first is in equilibrium with the third, like a transitivity, the transitive property of heat. All right, so what do I mean by this? Well, suppose you have some block, and let's call that, let's not even introduce temperature yet. This has a certain temperature, but we're not going to talk about temperature yet. And here we have something, another block. Let's call this blocks of metal. We just make it all the same metal if you want, iron. And what one does is connect these two thermally so heat can transfer back and forth, and connect these two thermally so heat can transfer back and forth. Call this System 1, System 2, and System 3. What this means is if System 1 is in thermal equilibrium with System 2, then System 2 is in thermal equilibrium with System 3. Okay, so if, and we're just calling thermal equilibrium, we're not defining temperature yet, we're just saying heat transfer. So if 1 and 2 are in thermal equilibrium, what does that mean? That means that no heat is being transferred back and forth. And if 2 and 3, systems 2 and 3 are in thermal equilibrium, no heat being transferred back and forth here, so everything is at equilibrium, then 1 and 3 are in thermal equilibrium. All right, so where did they come up with this? Well, suppose that you have two systems here, 1 and 3, and you somehow want to see whether in thermal equilibrium. Is there like a thermal equilibrium instrument that you can use? No, but you can use a thermometer. So let's make 2 be a thermometer. So thermometer somehow measures equilibrium. So if you put a thermometer here and you get a reading, okay, so you get a reading there with a thermometer, and you put a thermometer here and you get a reading with 3, and the reading of the thermometer is the same when they're both in thermal contact, everything is equilibrium, then you know 1 and 3 are in thermal equilibrium. Or let's define a temperature scale. 1 and 3 are the same. Let's introduce temperature. Temperature. If 1 and 2 and 2 and 3 are same temperature. So that's a Zeroth Law of thermodynamics. It essentially defines how you can say two things, say 1 and 3 are thermal equilibrium. You introduce some sort of scale, and with thermometer like a mercury thermometer, or in fact you can use an ideal gas, PV equals nRT, define temperature that way, the ideal gas thermometer. But it just gives you an idea, if this reads the same as this, then 1 and 3 are at thermal equilibrium. There'll be no heat flow transferring back and forth. All right, so that is the Zeroth Law of thermodynamics. There is, if one thing is in thermal equilibrium with two different things, then those two different things are in thermal equilibrium. Okay, now let's talk about the second topic of this lecture, and that is the entropy of chemical reactions. Oh, finally, as chemists, we're going to talk about chemistry. All right, because entropy is a state function, delta S is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. Okay, now note that this does not have any deltas. Let's contrast and compare there with, for example, the standard enthalpy of a reaction is the standard enthalpy of formation of the products minus the standard enthalpy of formation of the reactants. On the other hand, now we have the entropy, and let's make this a standard entropy of the reaction. It's just now the entropy, the absolute entropy of the products minus the absolute entropy of the reactants. And these you can determine absolutely. There's nothing relative about them. You don't have to refer them to the standard state, because the entropy of the products and reactants is 0 at 0 Kelvin. Okay. Now, what exactly standard state? Well, standard states, well, you're free to describe a standard state. So let's describe a standard state for chemical reaction to be 1 bar. Now, bar is a measure of pressure, And it's very similar to the atmosphere pressure unit that we've talked about in introductory chemistry and used so far. But it's a little different, just enough different to make a difference. So 1 atmosphere is 1.01325 bar. So an atmosphere is a little bit more than a bar. Okay, so if we're real physical chemists, we're going to use 1 bar as a standard state. But if we're sort of introductory level students, we can use 1 atmosphere. Now the point is that the standard, see that 0 means standard entropy. So although we don't have to calculate standard entropies because we have an absolute value, nonetheless we'll define an entropy change as standard as 1 bar. So the entropy of 1 bar of the products minus entropy. If we define our standard state not to be 1 bar but 1 atmosphere, then the standard entropy change may very well be different because we have a different standard state. All right, so different standard states or different temperatures or volume changes, what you can do is if you're not at the standard state, you convert to the standard state, both the reactants and products, and then you can calculate the standard entropy change. And here are the 2 important equations one uses to calculate entropy changes going from one state to another. This is the entropy change, heat capacity times the natural log of the final minus over the initial temperature, or the entropy change is the minus nr log of the final pressure over the initial pressure. Now just to show you that this is going to make a difference, let's do this example. What's the difference in the standard entropy of formation of 1 mole of gaseous water if the standard pressure of 1 atmosphere is used instead of 1 bar? Assume all gases are ideal gases. So for example, if you say that delta S0 is some number, that doesn't mean anything unless you specify what the standard state is. So you must specify what standard state is, because this is meaningless unless you say what the standard state is. If you have a different standard state, you'll get a different entropy for the reaction. So the problem says, well, we're physical chemists, so we are going to use 1 bar. But suppose somebody used 1 atmosphere instead, then this delta S0 will be different if the 0 refers to 1 atmosphere. And let's actually just calculate that, what the actual difference in the standard enthalpy of formation will be. All right, so you remember, let's just put a line here. So what chemical reaction are we talking about? We're talking about the standard entropy of formation. So remember, entropy of formation, you take of gaseous water. So we're going to take, write down the reaction for the entropy of formation of gaseous water from its elements. And this goes to H2O gas, and this is a gas also. All right, so there's a chemical reaction. And what we're going to assume here, let's see, let me check my notes. All right, so let's say this is, say, 1 atmosphere. And this is all 1 atmosphere. So this is the entropy change, standard entropy change when using 1 atmosphere. And what we want is the same reaction. Sorry, that's not O. What we want is the same reaction going here, H2O, where this is 1 bar, and these all here are 1 bar. And the entropy change here, delta S0, this will be at 1 bar. All right, so we want the see how the standard entropy will change when you use 1 bar versus 1 atmosphere. So how do you think we're going to do this? Well, we're going to write a thermodynamic cycle. First, we'll take the reactants in 1 atmosphere, and we'll take those to 1 bar, from 1 atmosphere to 1 bar, and that will give us some entropy change. And how do we do that? Well, here we go, entropy change, right there. See, pressure change, we can calculate the entropy change. All right, so far so good. So call this delta S1. Then here's the standard entropy. Now we got the products. Let's take the products down to 1 atmosphere. Call this delta S3 for the 1 to 3rd step. So now we take the product from 1 bar to 1 atmosphere. A pressure change, which we can calculate the entropy change there. So the problem asks, what is the difference between these two quantities when you calculate it this way versus this way? All right, it's a thermodynamic cycle, so that delta S, the standard entropy of that reaction at 1 atmosphere, will be equal to delta S1, taking it up to 1 bar, plus standard entropy change of the reaction at 1 bar, plus delta S3. So entropy is a state function, so the entropy change going from here to here is equal to the entropy change that plus that plus that. And that's just what we've written. Now, the problem asks to, what's the difference in the standard entropy of formation of these two processes? I didn't really say what minus what. So let's say, what did I do? Let's do, say, delta S0 at 1 atmosphere. Standard entropy when you have a standard state of 1 minus the standard entropy when you have a standard state of 1 bar. That is equal to delta S1 plus delta S3. All right, let's look at delta S1. What are you doing with delta S1? All right, so here we're taking a gas here at 1 atmosphere, hydrogen, putting it 1 bar, and here we're taking a half a mole of this gas at 1 atmosphere and putting it at 1 bar. And we said we can calculate those energy changes by this, or those entropy changes by this equation here. And we want to do it 1 mole of gaseous water. So we have 1 mole of this being produced. That means we have 1 mole of this and a half a mole of this. Okay, so delta S1 will be, let's do the hydrogen first, 1 mole. Do I have to keep, what do you think? Should I have unit? All right, I'll put units in. 1 mole. And note that's a minus sign. There was a minus sign here. Don't forget that minus sign there. Okay. N are 8.314 joule per mole Kelvin times the natural log of the final pressure, 1 bar, over the initial pressure, 1 atmosphere. Okay, so we've done hydrogen. We took it from 1 atmosphere to 1 bar. Let's do oxygen. That'll be the second term that contributes to delta S1. Okay, minus a half mole. I'll omit the units for this one. 8.314 times the natural log of 1 bar over 1 atmosphere. That's delta S1. That's that one. Let's look at delta S3 plus delta S3. That's for that second step. Here we're taking 1 mole of water at 1 bar and converting that to 1 mole of water at 1 atmosphere, a pressure change. Okay, so delta S3 will be 1 mole of water. Don't forget that minus sign. 1 mole of water times 8.314 joule per mole Kelvin times the natural log. Our final pressure now is 1 atmosphere. Our initial pressure is 1 bar. So we started at 1 bar and now we're going to 1 atmosphere. Okay, we can pull these things out. let's see, this is minus 1. Pull this out. Well, before we do that, let's make this a little easier here. So sometimes it's useful to do manipulations algebraically before you actually pull out your calculator and do some. So let's just do that. So here, there's 1 bar, 1 atmosphere, there's 1 atmosphere, 1 bar. Let's flip this over. And so let's make this minus natural log of 1 bar over 1 atmosphere. So we got natural log 1 bar atmosphere, 1 bar atmosphere, 1 bar atmosphere. So now we can combine all these terms. All right, so well, let's try to do it here, see if we have enough room. Equal. All right, so natural log of 1 atmosphere over 1 bar. So we pull that out. Let's pull out R, 8.314. And now what we're left with is minus 1. Minus 1/2. And now I've got to be careful here. There's a negative, and that's a negative. That cancels out the negative, so this would be plus 1. Slight mistake here. I've changed this to 1 bar per atmosphere. So let me just rewrite this as 1 bar over 1 atmosphere. Okay. So this is 1/2. So go down here. We have, and don't forget the minus sign here, 0.5 mole. Just rewrite everything here. 8.314 joule per mole Kelvin times the natural log of 1 bar divided by 1 atmosphere. It'd be nice if we had the same units here so we can cancel that out. Let's just see if we can get that. All right, entropy of chemical reactions. Here we go. No, not quite yet. There we go. 1 atmosphere is 1.01325 bar. So we can substitute 1 atmosphere for that. So this is minus 0.5 mole. 8.314 joule per mole Kelvin times the natural log of 1 bar, and we said 1 atmosphere is 1.01325 bar. All right, finally we can cancel those things out. We put all this into our calculator and we get 0.0547 joule per Kelvin. Note that this number is less than 1, so the logarithm will be negative, which will cancel out that. So, and what was this for? This was for the standard enthalpy change when we used 1 atmosphere minus the standard entropy change when we used 1 bar. So this shows that depending upon what you define as the standard state, you'll get a different number, because the difference here, if they were the same number, you get 0, but in fact it's a small number, but nonetheless significant number. So if you are working in research and you publish some information about enthalpy or entropy or some thermodynamic quantity to standard state, make sure you always specify what the standard state is. Okay, that's it. I hope you enjoyed listening.